Hi there, this is Nick, and this is the video screencast for Lecture 5 for CS107 on Monday, January 21st. So today we're going to continue our discussion of C strings, and we're going to in particular dive into more detail about how C strings are represented under the hood in memory. So the plan for today is we're going to start with a recap of the string operations that we talked about last time. We'll show you a quick demo of some memory errors that can come up in your programs and how you might be able to resolve them. And then we'll move on to some new topics. We'll talk about arrays of strings. We'll do a practice problem to pull together all of the string concepts. And then we'll move on to talk about pointers and how strings are represented in memory. So let's get started with a recap from last time. So last time we talked about how C strings are just arrays of characters ending with a null terminating character. This is how we know for any C string where the string terminates. And string operations, such as strlen, use this null terminating character in their operations. For instance, strlen counts up the number of characters it sees before reaching a null terminating character to figure out the length of the string. And we talked about many different built-in string functions that we can use in C. Functions like strlen for getting the length, strcomp for comparing strings, strchar and strstr for searching within a string, strcopy for copying a string from one place to another, strcat for concatenating strings together, and finally strspan for looking at what characters are at the beginning of a string. One other topic we also mentioned was how C strings are passed as parameters. We said that regardless of how you create the string, whether you create it as a char array or you create it by saying char star my string equals something, that's a string literal, when you pass a string as a parameter, it is always passed as a char star. But char star still lets you use bracket notation to access individual characters. Now, you might wonder how this is, and we'll see why this is later today. But you can see that we can use the bracket notation on a char star just as we might on an array. Now, one other thing we mentioned from last time was the risk of writing into memory or accessing memory that doesn't belong to us. And as we said last time, it's your responsibility to ensure that memory operations you perform don't improperly read or write memory, whether it's copying a string into a place that doesn't have enough space, or asking for the length of a string that's uninitialized or that doesn't have a null terminating character. Now, there's a tool called Valgrind that is helpful in potentially helping track down memory-related issues in your code. We're going to get more practice with Valgrind when we talk about dynamically allocated memory in future lectures, but I want to introduce you to Valgrind today, and you'll also get more practice with using Valgrind in labs this week. So I'd like to show you a quick demo of a program that exhibits some memory errors. I'm going to exit my presentation. I'm going to open a terminal window. Now, one of the things that's handy when working and debugging a program is to actually have more than one terminal window open at a time. It's easy to do this in most terminal programs. In this case, on a Mac, I can go up to the right-hand corner and just go New Window. And I can make a second window, and I can SSH into Myth using both of these windows at the same time. So I'm going to minimize my presentation window, and I'm going to put these side by side, and in here I'm going to SSH into Myth, and I'm going to do the same thing on the right side. Okay, so I'm logged into Myth, and I'm going to first clone the lecture code for today. The way to do that, in case you forgot, is to say cp-r, and then the path to the lecture code, which is AFS-IR class CS107 samples lecture 5. And I'm going to copy it into my current directory. Great. So now I can see the same files in the other terminal window on the right because they're both views into the same set of files, which is really handy. So I'm going to cd into lecture 5, and I'm going to open the memory errors program, which is a program I can actually do ls to see what's in here. I'm going to open memory errors.c. Okay, and I'll make this a little bit bigger. Now we can see this program is a program that has two functions that exhibit some memory errors that you might run into. The first one, error 1, calls strcopy on a destination that is too small. So as you notice, string 1 is a char array of size 6, as is string 2. Too long string is a string of 7 characters, so there's not enough space in either of these to store this new string, but nevertheless, I call strcopy, copying too long string into string 1. And then we print out string 1 and string 2. So we'll see what happens with that in just a minute. Error 2 is a function that calls strlen on a string without a null terminator. The way that this works is I have a char array of size 10, and I use str_n_copy to copy in just the first 3 characters of this string Stanford. So it just copies in sta. And if you remember from last time, this does not copy in a null terminating character because the 3 characters it copies here are not null terminating characters. And it doesn't end with a null terminating character either. So when I ask for the length of the string using strlen, strlen is going to potentially read into uninitialized memory until it finds a null terminating character. So we'll also see what happens here in just a minute. In my main method, I'm going to call error 1, and later on we'll uncomment this to call error 2 to see what happens. Okay? So I'm going to first, over here on the right side, also cd into lecture 5, and I'm going to make. Looks like everything is made already. And I'm just going to run the memory errors program. I hit enter, and you can see that it executes error 1, so I'm going to scroll up so we can just take a look at error 1 as we work. And you can see that we try to copy in this string A, B, C, D, E, F, G, which is too big, but nevertheless it still copies everything in. And in this case, it actually overwrote a little bit of memory after string 1 in order to fit everything. So it still prints out for string 1, it still prints out A, B, C, D, E, F, G. For string 2, it prints out hello. We never modified string 2. And then it prints out this done message from the main method. Okay, so let's try an even longer string. If it doesn't seem like this does anything bad, let's try something even longer. So I'll save over here, and over on the right side I'll make, and then I'll execute the memory errors program again. This time something really interesting happens. We notice that for an even longer string, it still copies the entire thing into string 1, way overwriting memory after string 1. And in this case, it overwrites so much memory that in fact it prints out string 1, which is the whole alphabet string so far, and it prints out string 2, which has now been also overwritten to contain QRS. Now what's happened here? Well, the strcopy overwrote so much memory to fill in this entire string that it actually overwrote the memory associated with string 2 in addition to string 1. And so string 2 is now QRS even though we never changed string 2 in our code. So it still prints out the done message. Let's try an even longer string. I'll save it over here. And I'm going to make the program and run it again. Now this time, we've overwritten so much memory that the program actually crashes. You can see that it prints out the entire alphabet string, which overwrote a ton of memory. It even overflowed the entirety of string 2 as well with the rest of the alphabet. And then it can't continue because we've overwritten too much important memory, and we crash with a stack smashing detected error. Stack smashing means that we've corrupted or overwritten so much important memory that our program cannot proceed, and so it crashes. You notice that it does not print out the done message as it did before from main. It does not reach that line because it crashes. So that's an example of how strcopy can overwrite important memory in our programs. Now let's take a look at error 2. I'm going to change main to execute error 2 instead of error 1. I'll save it over here, and I'll make over here. Now, let's take a look at error 2. As a reminder, error 2 calls strlen on a string without a null terminator. So I'm going to run memory errors again. And you can see the string length is actually 3 in this case. Now, why is it 3, which is actually correct? It's 3 because as soon as it got into uninitialized memory, it seemed to have found a null terminating character by coincidence. It's not necessarily there, and in fact, sometimes if we run it again, it may give us a different answer, but it looks like in this case, it still remains 3. But behind the scenes, there is a memory issue going on here where it accesses uninitialized memory in search of a null terminating character. But it might not always exhibit issues, as you can see here. So now that we've seen some of these memory errors, the question is, how might we track down and resolve these issues? Well, there's a tool called Valgrind, and Valgrind profiles or scans the memory usage of your program to alert you to any potential issues, and in some cases helps you resolve them. So the way that you run Valgrind is you use the same command you might execute to just run the regular program, but you put Valgrind before it. So in other words, I'm going to type Valgrind here, and I'm going to run this program in Valgrind. What happens next is the program will run, Valgrind will monitor it as it's running, and it will alert us to any potential issues. So I hit enter. You can see that if I expand this window a tiny bit, you can see that it still outputted the printf statements just as normal. It outputted error 2. But then you can see Valgrind outputted an error message right here. It says conditional jump or move depends on uninitialized values. What does this mean? Well, it means that there was code that was executed that depends on uninitialized or garbage memory. And it actually shows us where this occurred. Main line 39, which calls error 2, and at line 33 in error 2, which is right here where it calls the strlen function, in strlen it turns out there's code being executed that depends on uninitialized memory. So this helps us narrow down the issue, and then we can go in here and say, oh, it looks like we're referencing garbage memory, we can fix it. So Valgrind is a really helpful tool to run frequently to detect any potential memory issues. Now, one downside of Valgrind is that it can't detect all issues. In particular, Valgrind can't really detect overwriting stack arrays. There are a variety of complicated reasons for this, but for example, if I go back to my memory errors program and I run error 1 and instead of error 2, and I go back to the shorter string, which still overwrites memory but maybe doesn't cause any issues, I make, I have to comment these. And then I make, and then I run Valgrind on memory errors again, you can see this time Valgrind actually says that everything looks okay. So unfortunately, Valgrind can't always detect every memory issue, but it's still very useful to run for some types of memory issues to detect them, and you'll get more practice with this in lab this week. Great. All right, so let's go back to the slides. So that's an example of some memory errors that can occur in your program and how Valgrind can help. Next, I want to talk about arrays of strings. In your program, you can store an array of strings using this syntax. It's very similar to making an array of characters, except instead of the type being char, the type is now char star. So in this case, string array is allocated as an array of strings that stores 5 char stars. Now, one important note is that this array does not store every character in every one of these strings. Rather, it stores 5 pointers to strings. You can also make an array of strings using the following shorthand, and just like for char arrays, C will intuit how much space is needed for the array. In this case, there would be 3 elements. And like you might expect with arrays, you can access each string using bracket syntax, in this case to print out the first string. And one important note is that when an array of strings is passed as a parameter, it is passed as a pointer to the first element of the string array. This is what we talked about a little bit last time. When you pass an array as a parameter, it just passes a pointer to the first element. And so what this means for string arrays is a pointer to the first element is a pointer to a char star, which means that the parameter type is char star star. You can also write it as char star with brackets, but really under the hood, it's a char star star. And this is exactly what argv is in the main function. So now I want to pull together all these concepts and do a quick recap of last lecture's concepts with a function that we're going to implement called verify password. Verify password is a function that should accept a candidate password and certain password criteria and return whether the password is valid. What it means if a password is valid is if it contains only letters in this valid chars parameter and does not contain any substrings in the bad substrings array. So let's see some examples of usage. If we made an invalid substrings array, for example, maybe we want to prohibit the user from having the substring 1234 in their password. If we call verify password on the password 1572, and we only permit them to have passwords containing the digits 0 through 9, this would be a valid password and it would return true because the password contains only these characters and it does not contain 1234 as a substring. On the other hand, if we call verify password on 141234, this still contains only digits 0 through 9, but it contains the substring 1234, and for that reason is not a valid password. So now let's jump over to the myth machines and actually write this program up. So I still have my two windows open from before. I'm going to quit out of that file over here, and I'm going to clear the windows. Now, since you're following along in the video, the best way to do this exercise is to try to implement the program on your own first, pause the video while you do that, and then resume the video when you're done. You can see in the Lecture 5 folder, there is a verifypassword.c file that you can use to implement your function. And so if you open that, you can see there's a to-do marking the implementation of verify password. So I'd recommend pausing this video, trying to implement this function yourself, and then resume the video when you're ready to see how we might work through it. Okay, so let's take a look at how we might implement verify password. So there are two criteria for the verify password function, as we mentioned before. A password has to contain only characters in valid chars, and it cannot contain any of the substrings in the bad substrings array. So let's take each of these cases one at a time. I'm going to remove this starter code, and the first thing we're going to do is check password contains only characters in valid chars. Okay, so that's the first check we want to do out of two. Now, how do we check that it only contains characters in valid chars? Well, let's pull up the reference of all of the string functions that we've gone over already and see if any of these can help us. So we're not doing length or comparison. We're not really doing a search for characters or strings. We're not copying or concatenating, but we might be looking at string spans here. As a reminder, string span returns the length of the initial part of the string, which contains only the characters in the second string. Now this might come in handy here because what we can do is we can see what the length is of the initial part of password that contains only characters in valid chars. So let's do that. We can say int valid length equals stir span password valid chars. So this will tell us the length of the initial part of the password that contains only characters in valid chars. Now, what do we want this length to be in order for the password to be valid? Well, we want it to be the length of the entire string. The reason for this is we don't want any characters to be outside of valid chars. And so we can say if valid length does not equal the length of password, then we know that it's not a valid password and we're going to return false. All right. Otherwise, we're going to return true at the end. So let's save this and let's exit out of Emacs and let's try making and running just this case to see if our password verification works so far. So I'm going to make it and I'm going to run verify password. Now the way that this program is written is main takes in the password you'd like to check. And actually I'm going to go back to the file really quickly to show you what main does. It requires the first argument to be the password you'd like to verify, and it has some hard-coded bad substrings, and it verifies the password, and it only permits the password to contain lowercase letters or the digits 0 through 9. So let's exit out. We've already made the program, so I'm going to run verify password, and I'm going to pass in the password 012. Whoop. Verify password. That password is valid because it contains only allowed characters. Now if I do 012 ABC, that should also be valid, but if I do 012 ABC and then capital A, that should not be valid, which is correct. Or if I do a symbol, that should also not be correct. Whoop, that is actually a special command. Let's do this. That's an invalid password. All right, so that actually turns out to be a hidden terminal command. So this shows that our checking is working so far. So let's go back into verify password and implement the second check that we need. So we've checked that it only contains valid characters. Now we need to check password does not contain prohibited substrings. So how do we do this? Well, we have an array of substrings and we also have the length of this array. In C, we have to pass the length separately because arrays do not know their own length when they're passed as parameters. We'll see more examples of why this is later. So the way that we can check these prohibited substrings is just loop over each string in the array and see if it's in the password. So we can say for int I equals 0, I less than num bad substrings, I plus plus. And inside this for loop, we need to check if this substring is contained in password. The best function to use for this is the stir function, which lets us search for one string in another. So the way that we can do this is we can say char star substir start equals stir, and the first parameter is what we're searching, which is password. The second parameter is what we're searching for, which is bad substrings I. Now what this does is it returns the pointer to the start of the first occurrence of this substring if it exists, or null if it was not found. So if it was found, that means that this password is invalid. So if substir start doesn't equal null, return false. And if it doesn't contain it, it's just going to keep looking through the rest of the substrings, and if it doesn't find any of those, then it reaches this last statement and it returns true. Okay, so let's save this. We'll clear the screen, we'll make our program, and then we'll run verify password, and we'll do 0 ABC. That should be fine. Now let's try one of the prohibited substrings. One of them was secret. So if we do verify password 012 secret, that's invalid. If we do 012 secret ABC, that's still invalid because it contains the substring secret. But as soon as we put another digit in there, like a 5, then it's valid because it no longer contains that prohibited substring. Cool, so this seems to be working. Let's try one more. We can try to put in the password substring that's also marked as invalid in our main function, and that's also invalid. Awesome. So we've implemented our verify password. Just to recap what we implemented, we implemented verify password where first it checks if the password contains any characters not in valid chars. It does this using the stir span method or function. And the second thing it does is it checks that the password does not contain any substrings in this bad substrings array, and it does this using the stir function. All right, great. So let's close out of this, and let's go back to the slides. So next, I want to talk about pointers. We're going to be using pointers a lot in 107, starting from this lecture. And so I want to start with a review and recap of pointers that you've hopefully seen in other classes. So as a reminder, a pointer is just a variable that stores a memory address. We're going to be emphasizing this really heavily in 106 or 107, where a pointer is just a number. It just stores a number. And because there's no pass by reference in C, like in C++, pointers let us pass around the address of one instance of memory instead of making many copies. What this means is, for example, if we allocate an array in one function, when we pass that array as a parameter, C will always pass a pointer to the first element of that array to save space. The cool thing about this is that this means one pointer, which is 8 bytes, can refer to any size memory location, which is pretty cool. Pointers are also, as it turns out, essential for allocating memory on the heap, which we will cover later in future lectures, and they also let us refer to memory generically, which we'll cover in later lectures as well. So let's review the syntax for pointers. If we have an int x equals 2, and we want to make a pointer that stores the address of x, we can use the ampersand operator, which means address of. So we say int star x pointer equals ampersand x. This would store the address of x inside of x pointer. If we have a pointer and we want to get the data it points to, we can use the star or dereference operator. And so if we say star x pointer and we print out that value, it will print 2 because that is what x pointer points to. Now this is much easier to understand with a visualization. So let's go through a sample program that uses pointers to see how they're helpful in C. Now again, remember, a pointer is just a variable that stores a memory address. So we're going to draw out a stack diagram, which hopefully you've seen before is just a diagram of the variables that each function contains, and that's in memory. So if we start off with our main function, when we execute int x equals 2, this is going to make a new box in main's stack area that stores the value 2. when we call myfunc and we pass in the address of x, what this does is it makes a new stack frame for myfunc, and it initializes int pointer with the value of the address of x. What this means is that int pointer is essentially pointing to x. We can draw it with this arrow right here. And so when we go in and execute the code in myfunc, what this does is it dereferences int pointer, it follows the arrow for int pointer, it goes to that location, and it sets the memory there to be 3. So in this case, it would update that value in x's box in main to be 3. And then when myfunc finishes, its stack frame goes away, and all local variables go away. And then when we go back to main and print out the value of x, it's now 3 because myfunc changed it. It got the address, the location of x, and it went and changed what was there. Now in 107, we're going to be drawing even more detailed stack diagrams. And so I want to show you what those look like for the same program that we just traced through. In this case, we start off with a stack frame for main that doesn't have anything in it at the moment. Now in this stack diagram, we show the stack as just one big array of bytes. That's really what it is under the hood, and we want to get used to thinking about it as just one really big array of bytes. So when we start executing this function, we say int x equals 2. We now have one of the locations in the stack. In this case, I just made up an address, 0x105, that stores x, which is 2. Then when we call myfunc and we pass in the address of x, more stack space is made for myfunc, and the parameter int pointer is initialized with the value again of the address of x. So int pointer lives maybe at some address that I again just made up, 0xfe, and it stores the address of x, which is 0x105. This means that it points to, using this arrow, the memory that stores 2. So now I go into myfunc, I say start int pointer equals 3. Again, this just means go to the address that int pointer stores and update the data there to be 3. So we go to 0x105 in memory and change the value there to be 3. Finally, we finish myfunc. The memory for the stack area of myfunc goes away, and then we print out the value of x, which is 3, again because myfunc changed the memory at that location. Now, if we didn't have pointers, we would just make copies of the values. So in this case, if x was passed as just an int instead of an int pointer, we would allocate memory for x, which is 2. We would pass x as a parameter, which just passes the value 2 as a parameter. So when we make stack space for myfunc, val would store the value 2. And so when we go and update val to be 3, we just change the local copy that myfunc has instead of the copy in main. And so when we have the stack space go away, when myfunc finishes, main still prints out 2 because its value is still unchanged. Okay, so that's a recap of pointers. Now I want to take a quick break to talk about some announcements. The first announcement is that assignment 1 is due Monday, January 21st at 11:59 p.m. with a grace period until Wednesday, January 23rd. This week in Lab 2, you're going to be doing a lot of C strings practice of the material that we're talking about today and talked about last Friday. And assignment 2 is going to be released at the assignment 1 due date. Assignment 2 is all about C strings as well, so you're going to be writing some cool programs using C strings. That's going to be due a week from Monday, which is Monday, January 28th, with a grace period until Wednesday, January 30th. And along with assignment 2, we're also publishing a comprehensive style guide to give you guidelines and tips on how to write programs with good style in 107. That's going to be posted to the course website on the assignments page. That's all the announcements we have. So let's talk about the next topic for today, which is how strings are represented in memory, now that we've reviewed our understanding of pointers. So in C, when you declare an array of characters, contiguous memory is allocated on the stack to store the contents of this entire array. What this means is that there's enough memory allocated on the stack to store every character in the string, including the null terminating character. And the variable for the array refers to the entire array contents. It's not a pointer just to the first element. In fact, if you call size of on the array variable, it returns the size of the entire array, which is, in this case, 6. Now that's pretty cool. You might ask why we even need strlen if we can just call size of on a character array. We'll see soon why this is not always possible. But when you declare an array of characters, it creates memory on the stack to hold every one of those characters and the null terminating character. Now, an array variable refers to an entire block of memory, as we just discussed. For this reason, you cannot reassign an existing array variable to be equal to a new array. Just like here, you can't do this. This is not allowed. Additionally, an array's size cannot be changed once you create it. You must create another new array instead if you want an array of a different size. So that's character arrays. If you declare a car pointer equal to a string, just like this with a string literal, what happens is it turns out the string literal is not stored on the stack. Instead, it's stored in a special area of memory called the text segment. And the text segment is read-only. It's memory that does not belong to you, and so for that reason, you cannot modify memory in this segment. In the diagram at the right, I've shown that the text segment is just way further down in memory than the stack, but it's still, again, just part of this really big array of bytes. So the stack in this case would contain a variable for stir, maybe at some address 0x105, which I just made up, and it stores the location of the first character of the string literal, which is 0x10, which is down in the text segment that stores the character h. Now, as I mentioned, the pointer refers to the address of the first character. What this means is this variable is just a pointer. Stir is just a pointer. It's not an array of characters. And so when you call size of on this pointer, it returns the size of the pointer, which is always 8 bytes, no matter the total size of the string that it points to. So this is something important to keep in mind. A car variable, again, refers to just a single character. What this means is you actually can reassign an existing car star to be equal to another car star if you'd like to, like in this case. You can also, as it turns out, make a pointer equal to an array. What this does is it makes a pointer to the first element in that array. If you'd like to manage that array as a pointer instead of an actual array, you can do that. It just means that pointer on the right stores the memory location of the first element in the array, in this case 0x100. Now there are some other syntaxes that are equivalent to writing this line. You can also say car star pointer equals ampersand stir bracket 0. That also does the same thing. It gets the address of the first element. You can also do ampersand stir, but this is kind of confusing syntax, and we tend to try to avoid this if possible. So now that we've talked about how character arrays and car literals are represented in memory, I want to talk about pointer arithmetic. When you do pointer arithmetic, for instance, when you add to a pointer, you are adjusting the pointer by a certain number of places. What I mean by a place is it's the size of the type of data that the pointer points to. In this case, the size of what the car star points to is 1, because a car is 1 byte. So when you say stir plus 1, what this says at a high level is I want stir 2 to point to one place after stir right here. And so what C does is it looks at stir. Stir is storing 0xff1, which is the address of the letter A, in the text segment. And so stir 2 will equal one place after stir 1. So it will equal 0xff2 because that's where the next character is stored. Similarly, when we say stir plus 3, this says I want stir 3 to point to 3 places after stir does. So stir points to here. I go 1, 2, 3, and it will store the address 0xff4, which is where the L lives. And so when I print out these different variables, the first one will print out apple, the second one will print out the string starting at 0xff2, and the third one will print out the string starting at 0xff4. So this is what the pointer arithmetic is doing. Now it's important to stress, and we'll talk about this in future lectures as well, that you're not adding 1 byte or 3 bytes all the time here. What do I mean by this? Well, let's take a look at an array of ints. We haven't talked much about int arrays, but it turns out that they work exactly the same as car arrays. If I have an array of ints and I have nums pointing to the start of that array, which would be 0xff1, you'll notice I can say nums2 equals nums plus 1. Again, what this means is I want nums2 to point to the next entry after nums. Now the next entry after nums, it turns out, is at 0xff5. Why is it ff5 instead of ff2? Well, it's because an int is 4 bytes big. And so ff1 stores 52. This 52 takes 4 bytes to store, and so the next int is stored 4 bytes away at 0xff5. So it's not always adding 1 byte, it's adding 1 place, which is equal to the size of the type it points to. Similarly, nums plus 3 is 3 places, 1, 2, 3, which is 0xffd. So C adds the size of the type that it points to when doing integer or when doing pointer arithmetic. Okay. You can also use bracket notation with a pointer, as well as an array if you'd like. When you're doing bracket notation, you're actually performing pointer arithmetic and dereferencing the pointer at the same time. So if you say stir bracket 2, this gets the character at index 2. But you can break down this syntax into an equivalent syntax of star stir plus 2. What's going on here? Well, this is the equivalent of saying I want to go 2 places forward from stir, and then I want to dereference it. And so in this case, going 2 places forward from stir is 1, 2 to 0xff3, and then I dereference to get the p character and save that into third letter. So bracket notation is just advancing the pointer and then dereferencing. Next, I want to talk about how strings are passed as parameters. When you pass a char star as a parameter, it turns out that C makes a copy of the address in that pointer and passes it to the function. This means that they both refer to the same memory location. So for instance, if I have char star stir in main equal to apple, and I pass that char star as a parameter, it passes the same address that is stored in stir. So for example, stir over here maybe stores the address 0xff1 for where the A lives in apple. When I pass it as a parameter, it just passes this address. So this same address is stored in my stir, which maybe lives at some address like 0xfe. So this means that both of those variables store the same address and therefore refer to the same memory location. Now, when you pass a char array as a parameter, C makes a copy of the address of the first array element and passes it as a char star to the function. So what does this mean? If we have a char array here that stores apple, we saw before that this means that we have space on the stack to store every character in apple, right over here, A-P-P-L-E, and the null terminating character. And stir refers to all of this memory. When we pass this array as a parameter, C tries to save space, and it passes a pointer to the first element in this array. This pointer would store the address of A, which would be 0x100, and that's exactly what my stir stores, 0x100. Now, it's also the same if you do this. You can also say char star ARR pointer equals stir. Again, as we saw before, this makes a pointer to the first element in the array. And then we can pass that as a parameter, and it just passes that address as well. This is the same thing. Now, because you pass a pointer to the first element, if you modify the characters inside the other function, it will persist these changes back in main. So as an example, if we say my stir bracket 4 equals the character y, what this means is advance my stir 4 places, dereference, and store the y character there. So if we walk through what this does, my stir stores the address 0x100, advance that 4 places. So that means 1, 2, 3, 4. So we're now at 0x104. Dereference that address, go to that actual memory location, and put a y there. So this looks like this. We would replace the e with a y. And this modifies the memory in main for the original stir. So when we print out the string back in main, it would print out apply. Now, one important consideration here is that because we just pass a pointer to the array instead of the array itself, we can no longer get the full size of the array using size of. This is because it's now just a char star, and size of on a char star always returns 8, which is the size of a pointer. All right, so these memory details explain why strings in C behave the way they do. First, we can modify a string created as a character array because its memory lives in our stack space. However, we cannot modify a string created as a char star because its memory does not live in our stack space. It instead lives in this read-only text segment area. We can set a char star equal to another value, like another char star, because it is just a pointer that we can reassign. However, we cannot set a char array equal to another value because it is not a pointer. It refers to a block of memory on the stack. Next, if we change characters in a string passed to a function, these changes will persist outside of the function because we pass the address of where the characters live. And when we pass a character array as a parameter, we can no longer use size of to get its full size because we're just asking the size of a char star, which is always 8 bytes. So these are the behaviors of C strings and why they are the way they are. Next, I want to really reinforce these concepts by actually walking through a string program and seeing what goes on with the memory for the strings. Okay. So now I'm going to minimize my slides, and I'm going to open another program from the lecture slides today, which is memory.c. Now memory.c is a program that does some short string manipulations, and I'm going to walk through what this program does. So first, it creates a character array called str1 that stores the characters high. It prints out the size of this character array, which we know from our previous discussion should print out the actual number of bytes that stores everything in this array. Next, it makes a pointer to that array called str1 pointer. As we mentioned before, this is going to make a pointer to the first element in this array. Then it prints out the size of that pointer, which we know should always print out 8 bytes, regardless of the size of the array, because array size does not get transmitted when you say size of a pointer. Next, we'll print out the contents of str1, which should print out high. Then we call modify first char. We'll see what that does in just a minute. And then we print out str1 again after modify first char finishes. So what is modify first char? Modify first char takes as a parameter str1, which is a pointer to the first element of our character array, and it prints out first the size of its parameter str, which again we know will always print out 8 bytes because the size of a pointer is always 8 bytes. Then it tries to modify the character at index 0 in str, and it changes that character to be lowercase h. Because again we pass the array of characters via a pointer to the first element in the array, this will change the memory all the way back in main. So modify first char finishes, we expect this second printf to print out lowercase h high, while the first one to print out uppercase h high. Now I want to actually use GDB to dig into the memory and see what's really going on here. So in my other window, I'm going to make, and then I'm going to run gdb memory. Now GDB has just started up running, but it hasn't actually begun executing the memory program yet. It's waiting for debugger commands before it starts running. So for instance, we would like to pause the program when it gets to main, for example, to see what's going on. So to do that, I can add a breakpoint at the main function by saying B for breakpoint, main, and that will add a breakpoint at main, in this case line 17. Now when I'm ready to run the program, I can just say run, and then provide any command line arguments here that I would need to provide. In this case, there are none, so I just hit enter. And now it starts running the program, and it pauses on line 17 where our breakpoint is. Now, if I hit next, it will go to the next line. One important thing to highlight here is that the line that GDB displays has not yet been executed. It is showing us the line that it will execute the following time that we execute next. So if I hit next again, it will actually execute line 18 and then pause on line 20 before it executes line 20. So now str1 exists. I can print out the contents of str1, and it says hi. Now I also want to keep a visual diagram of what the memory looks like from this execution. So I'm going to first try to find out the address of str1. I can print out ampersand str1 to get the address of the first element. which is 0x7, a bunch of f's, E9, F0. So let's go ahead and add that to our diagram. In the stack space, we have one of the addresses is 0x7, E9, F0. And at that address is the character H. Following it is the character I, exclamation mark, and then a \0. Now, what are these following addresses? Well, we can figure them out because the size of a character is 1 byte. And so this next address will be 1 byte more than the previous one. F1, F2, F3. Okay, great. And all of this memory is for stir1. Okay, so let's continue executing our program. I'm going to execute line 20 by hitting next, and now it prints out the size of stir1, which is 4 bytes, because we know the size of an array is the entire memory allocation for that array. Now I'm going to hit next again to create the stir1 pointer variable, and I can print out stir1 pointer, which is also high. The reason for this is when you set a pointer equal to an array, it points to the first element of that array. So stir1 pointer also points to H, and when you print it prints out the entire string up until the null terminating character. Now, what is the address of stir1 pointer? Well, it's E9, E8. Why is that? Well, let's write it in first before we discuss it. So 0x E9, E8, and that stores the value of the address of the first element in the array. So this stores the address of the H. Okay, now why E9, E8? Well, if you look here, the difference between E9, E8 and the next address, E9, F0, is 8 bytes. It turns out that 8 bytes, as we know before, is the size of a pointer. And so it needs 8 bytes space because it's storing 8 bytes for the pointer. And then as soon as we go beyond that 8 bytes, we get to the H. Okay, so this is stir1 pointer. Okay, so now let's hit next to execute the print statement. It'll print out the size of stir1 pointer, which is always 8. And then if we hit next again, we can print out stir1, which is high. Now we reached line 26, where it's about to execute modify first car. If I'd like to step over modify first car, if I want to execute the whole line 26 and just go to line 27, I can just hit next again. But in this case, I want to actually step into modify first car and go to line 13. To do this, I can use the step command, which is S instead of next. Next goes through the entire line and finishes. Step goes down into that line and lets you step through the execution of that line. So if I hit step, now we're on line 13 for modify first car. So now we're about to execute line 13. Before we do that, I can see that I have a parameter str, which is equal to E9F0. Why is that? Well, it's because we passed in as a parameter to modify first car stir1. Stir1 as a parameter is just the pointer to the first element of that array, which is E9F0. So let's add that to our diagram. So this is E9F0. And what's the address of stir? It is E9B8. Now you'll notice there's some space in between the memory for modify first car and the memory for main. That's just the way that the stack is organized. And so this is stir, and this whole block of memory right here is for main, and this block of memory right here is for modify first car. Great. So that's stir. Now if I hit next, it's going to print out the size of stir, which again we know is always 8 bytes because it's a pointer. Now we've reached the line 14. It's about to execute line 14. Now what line 14 does is it says, hey, stir, I want to get your 0th character position and set it to equal to the lowercase h. So let's break this down. Another way of saying this is it says, take the value stored in stir, add 0 places, dereference it, and then put a lowercase h there. So what I forgot to do was I can put in an arrow from stir up to indicate where it points to. Now what this bracket notation says is I'm going to go to the value for stir, which is E9F0. I'm going to add 0 places, so I'm going to stay there. And then I'm going to replace what's there with a lowercase h. So I'm going to erase this and put in a lowercase h instead. You'll notice that we changed the memory in main. This changes the actual data stored in the stir1 array because we have an address of where the memory lives, so we changed the actual memory. So these changes will persist. So then if I hit next to execute that, now the uppercase h has been changed to lowercase h, and so if I print out the value of stir, you can see that now it's lowercase h high because it's changed the data. So now if I hit next again, I can go back to main. I can execute line 27 by hitting next again, and now it prints out lowercase high for str1 because, again, the changes persist. So that's an overview of how we can diagram out the memory for our program. All right, so finally, I want to talk about pointers to strings. There are some cases in our code where we would like to modify a string's pointer itself rather than just the characters it points to. Now, what do I mean by this? Well, I want to give an example of a function called skip CS_prefix. The goal of this function is it should take in a string representing a class name, such as CS41 or CS107, and it should modify it to advance past the CS prefix, if any, in the string. So as an example, if I pass in the string CS41, skip CS prefix should modify the myStir pointer to advance 2 places past the CS prefix in this case. And so if I print it out after calling skip CS prefix, it would just print out 41. So the easiest way to understand why a pointer to a pointer is useful here is to diagram out what's going on in this program. So the code for this program looks something like this. I have a car star myStir that's equal to CS41. Then I call this skip CS prefix function and I pass in the address of myStir. That's because if I just pass in myStir, it will get a copy of the myStir pointer as a parameter, whereas I want to modify the original myStir pointer. Then it'll print out myStir after the function is called and it will return 0. Inside of skip CS prefix, we can see that we try to find the CS prefix in the string that's passed in, and we check if the prefix was found. Now I want to walk through this function line by line and show you what the memory diagram might look like. So when we start with myStir equals CS41, we create a new variable on the stack for main called myStir, and it's equal to some address of where the string lives in the text segment. So CS41 is in the text segment at some address like 0xf, and so myStir stores the address of where this string lives. Then we call skip CS prefix. Now our goal is to modify the value in this box right here, in location 0x105, to be 0x11. Now why do I say that? Well, the goal is that we want myStir to point to a string that is just 41 and then the null terminating character. We don't want it to point to CS anymore, so we want it to advance past the C, past the S, and we want it to point right here. So we want this box to store 0x11. If we just passed myStir as a parameter here, we would pass 0xf into the function right here. Instead, what we want to do is we want to pass the address of myStir, which is 0x105, so that this function up here knows where to make the modification. So that's exactly what we're going to do. When we call skip CS prefix, more memory is created on the stack for skip CS prefix, and we're passing the address of my stir, which is 0x105, and so that gets put inside the stir pointer parameter. Stir pointer stores 0x105. Now, its type is a car star star, a pointer to a car star. The reason is that it points to a pointer to a character. Now we'll see how this works by walking through the rest of the program. So now we're executing the first line of skip CS prefix. What happens is we say a new local variable called prefix equals stir stir. Now what we're doing here is we are searching for the substring CS inside of stir pointer string. Now we can't just put stir pointer here. The reason is that stir pointer is not a string. It's a pointer to a string. So in order to use it in stir stir, we have to dereference it to get the string that it points to. And then we can use stir stir. So in other words, we need to not pass in 0x105, but we need to pass in 0xf. So we call stir stir and we get prefix. Prefix should point to the first occurrence of CS in the provided string. So prefix should store 0xf because in the string that stir pointer points to, 0xf is the beginning of the occurrence of the CS substring. So prefix equals 0xf. Next, we go to the line here where we're checking if the prefix was found. So if prefix is not null, and if it equals star stir pointer. What this is saying is if this is the same, if this is pointing to the same place as the start of this string, that means that we found the substring at the start of this string. So if this is the case, we're going to dereference and get the string that stir pointer points to, and we're going to add a certain number of positions. In this case, we're going to add 2 positions because that's the length of CS. So what does this do? It says stir pointer, go to the location that you store and then add 2 places to that number. So we're going to go from 0xf to 0x11 because we again go to location 0x105 and we add 2 places, 2 characters worth of addresses to this number. So it goes from 0xf to 0x11. So now we're done with skip CS prefix. Its memory goes away. All of its local variables go away. And now we're back in main where we print out the value of my stir. My stir again has been updated because skip CS prefix knew where to go to find it and update it. So now when we print it out, it prints out the string 41. So this is an overview of an example of how pointers to strings may be helpful. Specifically, if you need to change where that string pointer points to. So if you need to change where my stir points to, you can't pass in my stir. You have to pass in the address of my stir so that a pointer to that car star can be used inside this function. All right, so just to recap the topics for today. We first started with a recap of the string operations we talked about last time. We went into details about how certain memory errors can manifest themselves in your code and how the Valgrind tool might be able to help. We then introduced arrays of strings and used all of these concepts so far to implement a password verification program. Then we did a recap of pointers in C. We took a break for some announcements. We talked about how strings are represented in memory. And then we ended with talking about pointers to strings and why they're useful in our program. Next time, we'll continue talking more in depth about arrays and pointers. We'll see you then.